followed by a seminar by Rogelma, then a coffee break, followed by seminars by Mateus, Rafael, and Carol, okay? And we are doing to try to end up earlier so you can enjoy the manifestation in Paulista. Unfortunately, you didn't came with the proper color. I suppose you're going to home to change and be properly with the uniform. That's obviously a red t-shirt. So today we're going to talk about another type of confinement instead of confining in solid state materials like nanotubes or graphene sheets or molybdenum disulfate sheets. We are going to confine in biological systems and ask ourselves, what does change? We are going to see two types of materials. We are going to look water confined in proteins and in the grooves of the DNA. But before that, wow, that was horrible, but anyway, we are going to remind ourselves that how we calculate the diffusion coefficient, that will be very important for us, and also the rotational diffusion, and how you can calculate the viscosity, and remind ourselves about Stokes-Einstein relation. That is the basic thing. Gustavo mentioned many times about the hydrophobic and hydrophilic idea. For us, the hydrophobic and hydrophilic, it will be related to the interactions with water. And in nature, we have super hydrophilic materials that completely wets, then normal hydrophilic that wets a bit, and we are here defining by the contact angles water does with these materials, but then you have hydrophobics when you have angles lower than 90 degrees and super hydrophobic materials. And more or less in this idea of the contact angle that we are going to define the hydrophobic and hydrophilic regions we have to analyze the behavior of water. So to understand how water wets a protein, we took a very small protein that's called TS-kappa. That's a protein from a poison for a scorpion. We put this protein in a box full of water. Here's the schematic design of this protein. This protein is composed of this type of amino acids. These ones are the hydrophilic ones, and these are hydrophobics. They are kind of mixed up along the surface of the protein, and we are going to look for the behavior of this protein when surrounded by two types of water models. So this is the model we discuss along the school a lot, the SPC water model. That's a very old model developed by Raul Grijeira, in which you have the oxygens, the hydrogens. The hydrogens have no mass, and they just have the charges, but the charges are localized in the hydrogens. And we have the TIP 4P 2005 that Paula mentioned many times, in which you have oxygen, the hydrogens, and you have a localized charge that have no mass but charge, and the oxygen have the mass, hydrogen have the charge. And they have slightly different parameters, and this is a model that have been widely used for many of the behaviors of water, and they reproduce reasonable well the behavior of water. For each one of those models, we are employing slightly different number of water molecules because we want to fill at the same pressure a fixed size of box. That's the reason why you have the interactions slightly different in these two models, so we use a slightly different number of water molecules filling up the box. And the first question you ask yourself is, when I have the protein inside the box, how the density anomaly changes by the presence of the protein. It's not how the protein changes, but how water changes because of the protein. So when I have the filled circles means protein with water. When I have the empty circles means bulk water. And one thing is obvious, that when you include the protein, you include the density, because you have less space for the water to be. So there is a shift in the value. But the second thing is there is a slightly change in the temperature of maximum density. And all the plots will be done in repetition, because I'm doing for SBCE and TIP4P 2005. But in both cases, we have this component of small shift. Also, you observe that there is a change. Here is the number of hydrogen bonds, and obviously when you have just water by itself, you have more hydrogen bonds, because part of the bonds will be water protein bonds, and that's the reason why when you have the protein, you have a decrease in the number of water hydrogen bonds in both models, with numbers that are slightly different for each one of the models. What you did next is that we decided to look what happens with the water in close contact with the protein. So what you did here is that you look to all water in the box. Now I'm just going to look what happens with the water that's close by the protein. And I have then to define what does means close by. Okay? In order to do that, I look to the radial distribution function, again, something that we have shown in this school many times, means that is the water, only water without the protein, radial distribution function, and for different temperatures. And you see that you have a first peak that roughly ends, that first layer of water molecules ends about 0.33 nanometers. And this is like the first layer of water in water, okay? So my next water will be more or less this distance. So you do the cut around the protein at this distance. It's rather arbitrary, because I'm taking a measure in the absence of the protein, but if I want to do a measure, I select a distance, and this is the distance I select, okay? A distance in which in bulk water, I will not have many layers of water. I will have one, maybe two layers when I'm close to protein. And then I look at this layer, okay? The density of water. So here's my protein. I take this distance from the protein, and I calculate the density at this layer, okay? Arbitrary, but it's the same arbitrary for every one of the lysozyme. This is the hydrophilic sites around the sites. So what I also did, here's this lysozyme. I calculate the density here. Here is the arginine. I calculate the density here. Always around the specific site, I calculate the density for distinct temperatures. And the first thing that shows in this is that as I increase the temperature of my system, the water goes away. So I become less dense in this vicinity of the protein, because these are hydrophilic sites, what means that the water wants to make hydrogen bonds, but if I increase the temperature, they break the bonds and they go away, okay? They prefer to make bonds with water, in the bulk water, than to be here. And this happens in the different levels, okay? Because we see different densities, because some of them are more hydrophilic than others. And the same thing happens for, this is for SPC water, and this is cheap for P2005. You see that's not the same result. What indicates that for hydration, the specific model you select for studying the system makes a lot of difference. For density anomaly at 4 centigrade, it doesn't, okay? The specific models, most of them reproduce density anomaly. But for studying hydration, the specific model makes a lot of difference. So it's important to test when you study a specific system, which model you're using with some experimental data, okay? But here, at least all the models of water are showing the same result. We increase the temperature, the water goes away. And when you look to the hydrophobic, something rather interesting happens is that it goes away, but then somehow at higher temperatures, it seems that you form, more water comes back. You start to have a threshold temperature in which you have this funny increase when you have this hydrophobic site. Somehow you start to bouncing back. Maybe because at this very high temperature, all the hydrogen bonds in the water region are disrupted, so now the surface of the protein is a locus that water, there is no competition between bonding with bulk and being this empty space surrounding the protein. And the same thing happens with cheap for P2005 water. So here is if I do an average between the two systems, you're going to see the hydrophilic have this that goes away, and hydrophobic has this small jump. Of course, the densities in the hydrophobic are lower. This is obvious. They don't do hydrogen bonds with the surface, so this is an obvious result. Was it's less obvious that you might find a region in which you were increasing the bond with the hydrophobic sites. And the same thing appears for P2005. Then we also look to the time. A very important quantity is the time you make hydrogen bonds. Because hydrogen bonds, they break and disbreak, but the lifetime, the time they last, is also an important information on how organized you are, okay? So here you decide to study the lifetime of water-water hydrogen bonds at bulk, means there, inside, far away from the protein, near the hydrophobic sites, and near the hydrophilic sites, okay? So here the solid line, as you see, it's the bulk. And what you observe is that only at very low temperatures, you see a difference between the hydrophilic and the hydrophobic. What's meaning here is that the hydrophilic side, the hydrogen bonds at lower temperature, they last a little bit more. So they are grabbed longer even than with water. So they favor to be with the hydrophilic sites than in the bulk water. And this might explain why we have the TMD that I showed before when you have the protein immersed having slightly lower temperature. See, this dashed is the lifetime of the bonds. These two other ones are the lifetime of water and hydrophilic and water and hydrophobic sites of the protein. So the lifetime that the water and hydrophilic, and water and hydrophobic sites. So inside the hydrophobic sites, inside the hydrophilic sites, this is the water lifetime. And here is for the dashed line is for the hydrophilic, and the slash lines for the hydrophobic site. Inside the water hydrogen bonds, and they last longer for the hydrophilic sites. And finally, the number of hydrogen bonds between water and hydrophobic and hydrophilic sites of the protein. So this is the sites in the protein, and this is water, and this, the water with the proteins, of course, you have for hydrophilic sites longer, but all they die out with temperature. That means that temperature kills the bonding in all the cases. Then we calculate the number of hydrogen bonds, water hydrogen bonds per water molecules versus temperature. So here's the water in number of hydrogen bonds of water in the vicinity of any of the hydrophilic sites, and you can see that again the number of hydrogen bonds, they die with temperatures, and the numbers are much lower than you expect for water hydrogen bonds. The same happens with the two models, because here I'm just comparing SPCE with TIP4P, and you can see this decrease. And then with the same water hydrogen bonds in the case of hydrophobic sites, obviously in the hydrophobic sites, the number of water hydrogen bonds are larger because water is not forming bonds with the sites, they are just packed inside this hydrophobic site. Okay, so this is not surprising. The same happens for the case of TIP4P water. In summary, when the water is close to the hydrophilic site, they make less water hydrogen bonds, but they bond with the site. And if put temperature, they go away. If we are close to hydrophobic sites, they make more bonds, they are more compact there, they make a lot of bonds when they are in hydrophobic sites because they don't have the hydrophobic sites to make bond, and they are compact. Good, we are making bonds here in this region. Here's just a summary in which I have average number of water hydrogen bonds in the hydrophilic sites, that's lower, in the hydrophobic, making an average of all the different amino acid sites. And this for the other models. So no numeric difference, but no difference in behavior, okay? Then we decide, this is to calculate, two calculations here important, the diffusion coefficient in this time of the time correlation function. This is a time and this is a diffusion value. And we are calculating here the diffusion in the three cases, the bulk water diffusion, in the hydrophobic vicinity and doing an average of all the sites, and the hydrophilic vicinity, we are doing an average with all the sites. You might remember when Paula mentioned that we are close to a glass transition, you find a fragile to strong transition, in which when you plot something as the diffusion against temperature or inverse of temperature, you get a kind of kink. Remember that? You have, and usually in her case, because she has a fragile to strong, is usually a curve followed by a straight line, okay? It's a fragile to strong. Here both are straight lines, so you have a change of behavior when you have the two vicinities. Not in the bulk water. See, bulk water is smooth. The diffusion is not even close to the diffusion anomaly. This is not a glass transition region. It's not that cool. It's room temperature and pressure. But you have a kink. okay? And the kinks for hydrophobic site and hydrophilic site are not in the same place, okay? So there is a change of behavior, one about 2040, roughly here, and one is about 2065, 70 here, okay? So there is a distinction. And the higher temperature is this for the hydrophobic side. So what this is telling us? It's telling us that the dynamic behavior of water close to the protein is influenced by the protein, okay? So it's protein making water to move differently, okay? The surface, so that's what to say. It is saying that if we are close to hydrophilic, you have a change in behavior that is different from hydrophobic. It's very different from hydrophobic, okay? Because even in the hydrophilic, to get into a region in which both kind of go to the same direction, above this temperature. It's kind of water in this region is want to go, but in the hydrophobic, no, it's completely different. So then we decided to calculate the mean square displacement, and this lines, the mean square displacement against temperature, okay? And you can see that we are about the same, you know, look here, oops, okay, what I did. So here, I should have put the same numbers, but we are very close to this region in this region, okay? Even though the graph, so this is the mean square displacement, and this is the mean square displacement of the protein. So the protein somehow is also moving in a kind of coordination with the water in the hydrophilic sites. Okay, so up to this point, they are together, and then each one goes in separate ways, you know, does its own diffusion. So while water is influenced by the protein is also influenced by the water, what means that when you discuss protein folding that happens in this area, water is also part of the process of the folding. Okay? So, lesson learned. Now the question is water in DNA. What are you going to do in DNA? Here's the DNA. And the DNA have two very interesting regions of confinement. You have a larger region where waters entered, okay, that call major groove, and a smaller region where water enters, that's the minor groove, okay? So we have this two distinct regions, one bigger, one smaller. And now we are going to do the following. You are going to put a DNA, a segment of DNA, inside a box with water, and we are going to observe what happened with the water within the minor groove and within the major groove, okay? Again, we are going to decide what means within, taking the ratio distribution function, cutting it at this, after the first peak distance, and use this as a distance in this direction, okay? Making like a box here. And look the water here, makes a box here, looks the water here. And we are going to do that with another model that's TEEP 3P water, because this model have been shown to be very good when you have some types of biological systems, works well, so we decided to use this with 52 molecules in a cubic box of this size. You know, this occupies a lot of the box. So the first thing we did was to look the radial distribution function of the water in this minor groove for two distinct temperatures. And as you can see, when you decrease the temperature, you have a very normal behavior, that is you decrease the first peak, what means that water, as increasing temperature, gets more spread about, okay? You have small peaks here because you don't have that many particles, and then you have a radial distribution function for the same. Then you do the same for the major groove. Again, the same behavior. You increase the temperature, you decrease the peak because you spread out more the particle. We also calculate the radial distribution, the mean square displacement, and we observe that here we are doing for different temperatures. We observe that not all the behaviors were thick behaviors, meaning that they are not straight lines. So you have some subdiffuse behavior here illustrated by T.7. As you might remember from Paola Gallo, I might have the diffusion D here. Mentioned, we only can write the diffusion if these have a linear behavior, but sometimes this expression, the mean square displacement, have something that have a fractional value here that can be bigger or lower than 1. When it's lower than 1, you have a subdiffuse behavior, and bigger, you have super diffuse. But then we cannot define diffusion. That's why instead of defining diffusion here, we just plot the mean square displacement, and we show that in some regions, in temperatures, the higher temperatures, we go as T, but at lower temperatures, you have a whole region in which you have a subdiffusive behavior for that. And the same applies for the major groove. You have a region of high temperatures in which we have a Fickian behavior, but at lower temperatures, the system just got subdiffusive. And the first one was bulk, minor groove, and major groove, and you can see here the same behavior. And here we're doing a plot in which we are plotting the diffusion coefficient we can get for the values we could get against the inverse of temperature, just to see if you can find any fragile to strong behavior. And you have here the bulk water, no transition, just a smooth curve. Then you have water major groove, and you can see that you have a break, like you have a linear behavior here, strong behavior, and a fragile behavior. And then you have water minor groove, in which, again, you find the behavior, with a fragile to strong behavior. And here we do the mean square displacement, not of the diffusion coefficient, but with the hydrogen lifetime for the minor and major groove, in which you can see that you have some regions in which you change, like different dynamics changing, like we observe here, different dynamics changing in the behavior depending on the temperature. So even though the bulk water do not show any fragile to strong, as you confine, you bring water to a behavior that's supposed to happen in bulk water at lower temperatures. So this fragile to strong that you observe for super cool water, we are seeing in the major and minor grooves at room temperature. Confining kind of bring you to a cool down region without losing stability. So we can access this region. That's why people looking for the second critical point, what they are attempting to do now is to confine water. Because if confinement allow me to go to lower temperatures without crystallization, then I will be able to measure the second critical point in the same way that confinement allow me to go from a normal water behavior to a fragile to a strong behavior for water. And this is it. So with that, we finalize the lectures, but now we are going to have exciting seminars with some presentations. Thank you very much. You have any questions? Yes. For which one? This one? I took these times. These are the real pods, like 0.8 nanoseconds. I did different, you're saying that for the, this one? No, this is the graph, this is the mean square displacement for each one of the temperatures. Yeah. Yeah, what you say, this is the mean square displacement. This is the mean square displacement for this different times. So if I'm plotting here, you're seeing which point I selected for this particular time. We did a cut for each one of the times in which we have the better straight line. Okay, we did an average for that. You mean when I want this point, where this point is located here. So we came here and we select the point in which we have more average, more stable with the straight line. More questions? If not, let's call Rojalma to give us her seminar. Acho que o cara tem que vir. Mas vamos ver se a gente acerta.
Acho que é isso, o HDMI. Escrever, colocar isso aqui, né? Porque se descarregar.
Hã? Todo mundo pode me ouvir. Vamos fazer logo antes do cara vir.
Tem que ser por cima, né? Do cabelo.
É. Põe por trás da roupa.
Você poderia colocar para mim? Pode ser aqui.
Do pointer para pôr no computador.
Tudo bem? Eu consegui o cabo daqui.
Márcia, o laser onde é? Não está a apresentação. Não é isso daí, não. Não está a apresentação. Sim.
Não é essa a apresentação?
Is this? Não está projetando lá no... Isso.
Ah, está projetando a tua tela?
Isso.
De tela?
Uhum.
Ah, tá. Você
É,
tem que,
Linux que tu tem?
É.
Function lá em cima.
você tem que mudar, ao invés de dividir a tela, espelhar a tela.
Isso é no function, pera um pouquinho. Isso não tem function.
Eu acho que é o botão do Windows, talvez, não?
Não, esse aqui. Ixi.
Será que não é o botão do Windows que funciona igual? Talvez?
Ah, agora foi.
De novo?
Ixi, selecione o dispositivo de áudio. Ah, agora foi.
Ah, ok.
Não tem áudio na apresentação, né?
Não.
Põe em tela cheia.
Okay. So it's a pleasure for me to be here. I am a professor at the Universidade Federal do Recôncavo da Bahia. And I'd like to thank to the organizers these events, invite me. And today I talk about the desalinization in graphene slit membranes, water mobility, and salt rejection. Before I talk with the subject this talk, I'd like to introduce you my collaborators. Marcia and Mateus is here, and this is João. My presentation has these steps. I start with the introduction and motivation, and next, our model and the molecular dynamics simulations. And we have the results and conclusions and perspectives. So, water scarcity is present in the world. This is a map with the 2040 water stress projectors by country. So we have the place with the extremely high projections for water scarcity, and Brazil appear with the low projection water stress. But in many places of the Brazil, it's very hard to the people to find water, and it's a very important problem. What can we do about this? So how much water is on Earth? We have only 3% is fresh water and 2% frozen in ice caps and glaciers. And only 1% is groundwater and surface water, and less than 1% is unusable. How about desalination of seawater? The problem is the NaCl is high, The NaCl is high soluble in water due to the strong electrocharge interactions. Water is polar, and it can to form hydrogen bonds and ion dipole interaction with the dissolved ions. So it's very difficult to separate the NaCl and the water. But we have the nanotechnology. Members based on nanopore graphene have been subjects in many works. Here we have the nanoporous graphenes by molecular dynamics simulations. Here we have graphene members, pore graphene members. We have simulation for member separation in porous materials. And so we have many works, we have this subject. Graphene is a material that is extracted from graphite and is made up of pure carbon. One of the most important elements in nature we find in daily objects, like the leader of a pencil. It's a common material. On the other hand, the graphene oxide is the oxide form of graphene. It is formed by the oxidation of graphene, which is cheap and readily available. Graphene oxide is easy to process, it is dispersible in water and the other solvents. What is our proposal? So graphene oxide membranes have been investigated as very promising candidates for water filtration and separation membranes. Here we have one work about this, but in this work, it's used the nanoporous graphene oxide. And our proposal is nano-slit graphene oxide. Our question, what are the effects of slit size on water mobility and salt rejection oxide graphene membrane? The influence of functional group parameters is investigated in the case. So we have this model we use in the work. Here we have the illustration of the system equilibration with the slit when it's closed. Here we have the infinity ensemble for equilibration, and we have the same pressure in both sides. After it has a different pressure, and the slit is open. Here we have the salt water and fresh water, and here the slit is open, and we have the salt water both sides. Here is a snapshot of model. We have the figure for the slit with 1.0 nanometer, and we have the slit with the is 1.5 nanometers. It's online snapshots, the simulation. Here we have the model we use in this work. Marcia told about this in your presentation. It's a SPC model. It's a rigid model and no polarized bonds with fixed bonds lengths and fixed bonds angles. This model is based on SPC model geometry, but with a different set of parameters. Here we have the force field parameters for the immediate simulations, molecular dynamic simulations. We use the potential, Lennard-Jones potential, and we have the table with the parameters sigma, epsilon, and charge of these parameters. The Lennard-Jones cutoff distance using this work is 1.2 nanometers. Here we have about the method and simulation details. We have many softwares for simulations, but in this work, we use lumps. Here is the steps of the simulation. It starts with the initialization, the energy, minimization, equilibration, production, and analysis of the data. We have the application in many studies. But in this work, we investigate the effect of slit size in the permeability and salt reject water. Here we have the results for the flow rate. Here we have the slit open with the press difference between the piston. And we can see that when the pressure is high, the flow rate is high too, obvious. But what happens with the permeability and salt reject in this case? Here we have the permeability. In this work, we use the model salt NaCl epsilon. It's a model of Marcia and Raul. And here we have the permeability for slit 1.5 nanometers. It is higher than the permeability for the 1.0 nanometers. But in the case of salt reject, for the slit 1.0 nanometers, the salt reject is higher than for slit the 1.5 nanometers. Here we use the 4 different pressures. And we can see that when the permeability is high, the salt reject is low. Here we study the effect of pressure on density distribution of water molecules. In this case, we have a slit with 1.5 nanometers. And we investigate the effect of press difference between the piston in the density water. So, and we can see here that for pressure of 300 bar, the density water is this, is in layers. While for press 400 bar and 500 bar, the water is this. Here is near for the piston 1. And the slit is in the position here. Okay? The conclusion, this work is this. Our molecular simulation indicate that nanoslits graphene membranes are able to reject salt ions while letting water flow at permeability several orders of magnitude high than in previous work with graphene oxide nanopores. Then we have investigated the comparison in graphene oxide nanopores and graphene oxide slits. We will carry out more simulations for different degrees of oxidation because the oxidation influences the process and smaller slits. This is the reference used in this talk. And I'd like to thank my university, Universidade Federal do Recôncavo da Bahia, the complex fluid groups of Marcia, and the SENAPAD and the LNCC for their support in the simulations. Thank you for listening. Questions? Okay, thank you.
We are going now to have, because we are early for the coffee break, so we can have one of the three or Rafael or Carol. Huh? Yeah, now. Okay. And also to mention that this work will also come to the support, Roselma will also come to fone. Levanta com fone e laptop.
O seu nome aqui, né? Põe. A sua tela está em estender, tá?
Aí dá para ir
Agora
para
sim.
a manifestação.
Vamos lá comer parte de mortadela, que tem uma parte não, um sanduíche de mortadela. Você pede uma mortadela vegana.
Não, acho que você vai ter que dar Windows ou Linux? Tem que fazer igual fez no dela. Você tem que ou duplicar a tela.
Function lá em cima ou Windows lá em cima. É Bell? É, tem que fazer várias vezes. Não foi? Ainda tá aí?
Tem que. Isso aqui tem que ficar no.
Não. Eu vejo, mas são rapidamente. Sumiu.
This. Okay. Okay.
Foi no Canvas?
Google. I surrendered myself to the Google.
Pablo Marçal falando.
That's bullying, in case you don't know. So I'm going to present you some, I think 2 lines I've been studying recently with some of my students and colleagues. But I want to introduce you some aspects of interface science that I think it's important so we can understand a little bit why we look for the pores we look in materials. So when we start thinking about projects and starting new simulations. So a thing that has attracted my interest recently is solid-liquid interfaces, because I see many interesting phenomena happening at these systems. So I think, okay, we can contribute a little bit, and once we started to simulate these things, I terribly regretted being able to do that, because it's so challenging, and we have so many things to look at when you are at interfaces. So book water is way more easier. If you go there, please stay there. Because in interfaces, there are other components, you know, like, of course, you can use these components to clean water, clean the surface itself. So as Gustavo was saying, the behavior, the interaction between 2 materials can lead to different behavior in the liquid interacting with the solid. So one very common thing happening when it rains, for instance, is that water droplets carries the dirt in the walls, for instance, like in this picture. This happens particularly because the walls can interact. It can interact like in many ways, but we separate. Again, there is no specific hint that if we separate materials into hydrophobic or hydrophilic, they will be actually precise difference between them, but they can behave like this. So most of the time you're gonna see, okay. No. Okay. You're gonna see a material interacting like this, so it will repel water, and sometimes it's gonna be like this. A better way to see this is like in this interaction, if you have like attraction, you're gonna have like this behavior when 2 materials are very attracted to themselves. And the other way to see this is like if you have a rejection type of interaction, so you have 2 materials being apart. So this is interesting. But again, we can define a parameter that actually separates hydrophobic from hydrophilic. So one easy way to do that is to find something that's visible to the experiment. So we like to use the contact angle as a definition of hydrophilicity, hydrophobicity. So if you find a contact angle that is larger than 90 degrees, you call it hydrophobic. If it's lower, you call it hydrophilic. Of course, there are other characteristics like the hydrogen bonds. If you have more hydrogen bonds between the solid and the liquid, you'll call it hydrophilic. If you have less, you call it hydrophobic. Also, we like to see at interface, if we find some depletion zone, if we find some lower density at the interface between the liquid and the solid, we will also refer it to hydrophobic. Otherwise, we call it hydrophilic. If there is a denser, a packed, dense region of liquid in the interface. So that's one thing. The other thing is that, again, it's kind of straightforward to look at the droplet at the solid interface, so you can measure this quantity, the contact angle. The apparatus will involve a CCD camera or something like this, and of course, if as smaller you go, if the droplet starts to be very small, you're gonna need some more sophisticated apparatus, but okay, the idea is the same. Again, we can go from hydrophilic to hydrophobic in a sense that we look at the contact angle, but this works for like smooth interfaces. If you start to look at interfaces that are not so smooth, there are different ways in nature of showing different surfaces, more rough surfaces. You're gonna find different states of interaction in which water can actually access the cavities of the surface. We call it Wenzel state. If it is more, if the geometry of the surface is in a different way, maybe water doesn't access the cavities, so we call it Cassie-Baxter. And there are different mixtures of assessing states in which we call different names. But the idea is that if you have a pattern, if you have rough surfaces distributed in a pattern, you have different ways of interaction, solid-liquid interaction. So in nature, we find these patterns, like the one famous example is the lotus leaf, when you have this very marked biological patterns. It looks like a pillar, so we've been trying for the last decades to reproduce these pillars in experiments and even industrial scale, so we would be able to actually repel water. It's quite hydrophobic interaction when we have these pillars. We can even do it like in experiments like these, so water would be highly repelled from the surface, and of course this have some nice applications for coating industry and many other things. So, okay, one thing that we try to look when you look at the interfaces is if the interface is actually rough or smooth. So we usually see graphene. Graphene is a very important material, being highly studied in the 2 to 3 decades. Last decades, and it shows impressive electronic properties. But we are more interested in the mechanical properties of graphene. You know, graphene is when you have carbon atoms distributed in a honeycomb lattice. The carbon atoms in graphene will interact through sigma-sigma, or the orbitals will interact through sigma-sigma interactions. It will make the graphene surface very strong to be tear apart, but very flexible. This flexibility makes difficult to see graphene as a very planar surface. That's why in experiments normally it's more common to see graphene in a more undulated way, or there are different, of course, different deformations, different conformations graphene can assume, but it's quite easy to see experiments to find this kind of undulated surface geometry. So it made us interested in this kind of behavior of graphene, so we were wondering how this distribution of carbon atoms would impact water flowing through the graphene, and this is more realistic. It seems more realistic to us to see water interact with undulated graphene and rough graphene. Of course, it's very hard to define roughness, so we try to start with a very controlled environment. This environment is basically based on wave functions, when we have this a parameter being the wavelength and the other parameter being the amplitude of the wavelength. So we're going to control those parameters and see how water moves towards the surface of graphene. The idea is that we can actually look at water entering the cavities. Of course, this is emulating a Wenzel state again, which permits water from entering the cavity, but a little bit different because now we have this, I wouldn't call this pillars, so it's a little bit different. If you open up a little this undulation, you're gonna see that water enters more, so it's gonna be a very strong, not very strong interaction, but you have more space for water to actually assume positions and geometries inside this kind of pores, all called channels. Okay, so, but the important thing is the definition of the contact angle. We see, as in the experiments, in simulation, it's also quite, it becomes more difficult when you go to nanoscale. So this is a nanodroplet, and the edges of the droplet, if you look at these interfaces here, the edges are not that smooth, so you're going to have to find a way to actually interpolate this and find a way to find the contact angle. Okay, so, but okay, we could find this. We could fit the density profile of the droplet along the whole simulation, so now we are able to find the contact angle. It means that when droplet walks over the graphene, of course, I only show you the good results, and these are for hydrophobic results. If you look at the hydrophilic ones, water will get a little bit stuck in the surface, but the hydrophobic interaction makes water a little bit loose over the surface, so water would go long distances. And an interesting thing is that if you change the distance between peaks, the wavelength of the wavelength parameter in the wave function we define to define the surface roughness. If you change it, if you increase it, and you don't need increase too much, like it's going from 0, I mean pristine graphene, to 1.5 nanometers. So the 1.5 nanometers will be the difference between two peaks here. You make water goes longer distances than if compared to the pristine case. The pristine case is more random, looks like Brownian motion. This is very interesting. Of course, we have to understand this. This is why we've been talking to Gustavo and Nicholas to see what we can construct this. One thing that we can look at is the impact of viscosity over the movement of the water. So if you look at viscosity, you have two profiles here. This is the height. We could also look at the wavelength factor, but if you increase height, you're going to see that an increase in the viscosity, but the increase in viscosity for, I think it's hydrophilic one, the black one, is larger than the increase in viscosity for the hydrophobic one. That explains why water would, go longer distances, because there is less resistance. So yeah, we kind of interpreted that in that way, but then the referees told us that this is just the properties of the droplet itself, so we should look at the interface between the droplet and the graphene. That's where we are now, trying to actually understand some structuration that will be an impact from the surface. Okay, but again, if you are at the solid-liquid interfaces, you can use it for other things than to accelerate water molecules. You can use it, for instance, to clean water. As Rogelma told you, we have some serious problems trying to provide fresh water for some regions in planet, and this is going even worse during the decade. So I think it's going to be even more important that we do some research in the cleaning process of water. So one thing is that in 2010, 2012, some groups came up with this idea that if you decorate graphene and you open up pores and decorate graphene with specific functional groups, you can either enhance water flux or hinder it. So one way to enhance water flux would be decorating water with these hydrophilic groups, attracting water to the pores. This will make a huge difference to the organization of water. And of course, if you want to repel a little bit water, you could use like hydrophobic groups, like this hydrogen-based, just hydrogenated pore. This will lead to states of high flux. Like in this comparison between hydrophobic and hydrophilic, they show that if you use hydrophilic pores, those decorated with hydroxyl groups, you could attain like one-third more flux than if you use hydrophobic hydrogenated pores. So, but why is that? Okay, if you look at the water passing through the pores, this is a density map exactly inside the pore when water is passing through. You can see that water organizes in different ways depending on the decoration of the nanopore. So if you have hydrogenated pore, it will make this circular shape. This circular shape will occupy less space. The idea of the authors is that if it occupies less space, it will pass less water molecules during time. So maybe if you decorate with hydroxyl groups, which is a hydrophilic group, you could open up a little bit the possibilities of the pore to actually transport water. We're going to see later that this is not exactly like that, but okay, it can work for some materials. Then if you are interested in different interactions between water and materials, you can look at graphene is very, monotonic, very monochromatic in this way. Like it doesn't interact with water unless there is actually a functional group. You could use different materials that are more interesting in terms of interaction with water. Marcia told us already that molybdenum disulfide would be an alternative, because if you arrange molybdenum disulfide in this way, like you have layers of molybdenum disulfide, you have layers in which you have hydrophobic interactions and also hydrophilic interactions. So in a material that doesn't need to be decorated, you could, for instance, open up pores and maybe find some way to, again, separate water from undesirable substances. The interesting thing about molybdenum disulfide is that if you place one layer on top of another, you can place it in different ways. This will make different interactions also. So if water wants to go like this in passing through the different layers, water will experience different interactions, being more attracted or more repelled, depending on the way you actually stack them one on top of another. We've been doing some research in this material for a time now, and we find that depending on this interaction between molybdenum or the sulfide atoms, you're going to have different interactions. But the important thing is that we have found some great rates of rejection compared to graphene. Not so great for flux. That's a problem of these materials, because it's larger, the pore. So we have this rule that if you increase the path in which water has to be transported during the filtration process, you're going to decrease the flux. That's an idea that has been explained in different ways, but in general, you use very, very small, very short materials. You make water be transported for very short distance because you want to increase the flux. That's why if you use many layers of materials, we've been showing that too, you're going to decrease the flux and, okay. But the idea, if you have one layer of molybdenum disulfide, you can actually push water, inside the pore. Then the pore has this hydrophobic interaction, and the hydrophobic interaction will expel water, and then water will be attracted again for the outer environment. Otherwise, you're going to have this different location. So you see, depending on the structuration of the pore, you're going to have different transportation states. That's the idea. And here we have this showing case that if you have different terminations on molybdenum disulfide, you can achieve transportation rates that are close to graphene, actually. I'm just going to grab some water. So, okay, we have these. And one thing that interested us is that if you can differentiate between graphene, you see, this is graphene, it's a permeation rate. This is molybdenum disulfide. And we never found, actually, molybdenum to be better than graphene unless we are in these very small nanopores. And as we increase the nanopores, we still get some diminished flux compared to graphene. Of course, in this graphic, this is something that scientists do sometimes that I don't know. We did that because if we put this from 0 to 70, this will be almost the same. But now we want to, focus on the differences. And the differences we find at the time that are mostly related with the fact that you have a larger peak of water density inside the pore in molybdenum disulfide, which is completely different from the graphene state. If you have water passing through graphene, water doesn't stay that much inside the pore. Water is just repelled. And that's why we found this larger flux in graphene. Also, the time water is inside the pore is related to the fact that we have salt in this solution. Salt, we have been doing some different, we have used some different valence salts, like sodium chloride, we have zinc and iron. And depending on the valence of the ion, we found different rejection rates, but the rejection is always larger for molybdenum disulfide. So that's a thing related with, of course, the structuration of water while passing through the pore, but also with the fact that you have charge. Now you have charge. João has showed that the charges are very important when you want to separate water from salt. And another thing that's very important, if you add valence ions, higher valence ions, you're going to find this, we call it clusterization or flocculation. That's phenomena happening in solutions, salt solutions. And if you have salt, you see salt is very spread through the simulation box and through the actual system in reality. So the difference in the rejection rates are most related to the fact that when you are trying to reject or trying to separate water from higher valence ions, you're going to separate actually a big components of this aggregations between the ions. While when you are trying to separate salt from water, that's a little bit difficult because salt is very spread in the solution. But of course, the search for new materials to desalinate water, clean water actually, goes to different materials, to different ways of finding now carbon allotropes being used as membranes. This is porphyrin, different porphyrins. If you, for instance, want to make matrices from these porphyrins, you can find a pattern that will be able to be used in membranes, and that's very interesting. You can even control the pore size of the membrane if you control the type of porphyrins you're using. We've been interested in this particular configuration because this particular configuration have been shown to be experimentally stable. So, okay, we saw this. This looks like a membrane. It's porphyrin based. Here is the porphyrin. Here is the carbon groups that aggregate the membrane. And this has almost 1 nanometer in diameter. If you look, it's 0.8 nanometers in this direction, 1 nanometer in this direction. So it looks like a pore that's being shown to be very efficient, separating water from salt, for instance. But of course, we also, as in this case, we are looking for different valence ions. And what we see is that if you, this is changing the pressure, of course. So we are in a lower regime. I think this should be 1, 2, 3 kilobars. And in 1 kilobar regime, you have, I think it's salt here. But this is the water saturation when passing through the pore. So you increase pressure, you make water less organized while passing the pore. So again, as we've been seeing in the school, the organization of molecules is related to the density, to the packing of the molecules in the solution. So if you have less organization, you're probably going to a state of higher general density. Of course, the local density is very high in positions like you have a hydrogen, because you're going to have some hydrogen bond formation here. Below you have the hydrogen density atoms, so you can see that the hydrogen are actually pointing through the membrane. There's a hydrogen in the middle and a hydrogen below and over the oxygen. So again, we have very nice transportation of water, increasing pressure, but there are some differences related to, of course, the valence of the ions. So the valence of the ions are again an important thing, because as we saw before, if you aggregate different valence ions, you're gonna see this flocculation process that will gonna make the passing of the ions through the membrane more difficult, even for graphene, you can see here. Okay, but just to finish in kind of a perspective way, as I told you, the idea of a circular pore is not that a great idea, because if you look at the perfect pore, if you try to find what will be the pore that will transport more water, it turns out that this group has used machine learning to find the shape of the pore that will transport more water and reject more ions. They found that the shape is not circular, it's not squared, it's not rectangular, nothing like that. It's a very strange shape, and this is related with the fact that you can transport more water in these pores and less ions. So you could try to find something like this in more conventional ways, but you see in circular pores you have the same available space for water and ions, so you don't actually make a big difference from the transportation of water and from transportation of ions. Of course, this is for pristine graphene. There are no functional groups here. I think if you compare to functional groups, that will be a little bit different. But okay, if you keep things simple as in graphene, you'd find different shapes. So I want to talk to you about this little project that I'm in now. So this is I'm starting to edit this magazine. It's paper in physics. I would invite you to submit your works there, because I think it's a very nice initiative. It's an initiative from South American scientists to South American scientists, and I think we have, as you know, the publishing process is a bit complicated these times. You have this huge amount of money from governments going to editors that sometimes are not that preoccupied to the quality of the science. So I've been involved in this project, and I think you should consider this in your next publications. It's an of course, we only charge for the editing. It's $200, but it's a very low cost for the quality of the paper compared to the other magazines. And Carolina is also involved in this project. Ezequiel has been editing also in the journal. But okay, this is a nice initiative. We've been seeing some surge, some increase in the citations, and of course the impact factor that not that all the time measure impact, but this is another discussion. I also would like to present to you the city we came from, Santa Maria. It's a beautiful city. If you want to visit, we have this beautiful campus there. So it's always some forest, some, you know, some. The campus has this amazing landscape. All that, of course, when it's not raining. But this is the lab. We've been changing configurations as water passing through graphene during the time, but we've been trying to do some nice work, and I would like to thank you. So that's it. Questions? No questions. That's it. Coffee break.